All right, so we'll go ahead and get started. Thank you all for coming. As you can see, we're going to be talking about econometrics today. So we're going to start by getting R installed if you were able to bring a laptop. R is really nice because number one, it's free. And number two, it does a ton of statistics, whatever you want. So it's a free statistical software. It has lots of usability. So you're going to go ahead and go to CRAN and download R. So we'll do this together. So you're going to go to this website, the cran.studio.com. And if you already have R, you don't need to do this, but I'm guessing most of you don't. So you're going to go there and then click whichever one applies to you. So for most of you, it's probably Windows, but if you're using Linux or you're on a Mac, you would choose one of those. So most of you are going to choose Download R for Windows, and then you're going to choose Install R for the first time. Okay, and then you want to go ahead and click Download R 3.4.4 for Windows. So when you click on that, you should get something that drops down executable. And I won't click on it because I already have R installed, but once that's down there, you're going to go ahead and click on that and then run that so that you can get R installed. Okay. So for those of you who just got here, you're going to this website. This cran.rstudio.com, and you're going to download R from there. Okay, so once you've got that installed, you can go ahead and download RStudio. And RStudio is a really nice GUI, the graphical user interface for R, so that you don't have to just type. So it has like point and click that you can do. So I'll show you what that looks like. So you're going to go ahead and copy that. So you can type that in. So that's rstudio.com, products, RStudio, hashtag desktop. Okay, so once you're there, you want to download RStudio. So you can go ahead and click on RStudio Desktop, and it will bring you down. Then you want to click on this download. Notice this is the free version. That's what we want. So you're going to click on that, download RStudio Desktop, and then keep clicking the things that say free. So then you're going to click that again, download. And then you're going to click whichever one applies to you. So most of you probably Windows. So this is for Vista 7, 8, or 10. I'm going to click on that. That'll have a drop down. This one takes a little longer to install. So once that's down there, downloaded, you're going to go ahead and run that to install RStudio. Which one? Oh, yes. Okay, any questions on that? Is it working for you guys? Looks like you're still getting there. I'm going to give you a little time to get caught up. And if you didn't bring a laptop, you can just sit and smile while everybody else installs it. Okay, so first you're installing R by going to cran.studio.com, and you want to basically just follow the prompts to install R for the first time. Then you're going to download RStudio and just keep clicking the things by free, and then you'll click download, you'll have your executable, and then you can run that. Okay, so we'll go ahead and keep going while that's installing. So let's go ahead and talk about, well, what is econometrics? So econometrics is fairly broad, but in general it's defined to be the use of statistical methods to analyze economic data. So basically it's statistics used for economics. Regression is very emphasized in econometrics, so if you have done any econometrics, you probably see it's kind of all about regression. Econometricians usually analyze what we call non-experimental or observational data. The idea here is that usually with economic situations, you don't have the ability to set up an experiment. So this is much more challenging because if you were able to, for example, with medical type data, sometimes they can actually have clinical trials and then randomly assign people to which group they're in. But in economics, usually we have no ability to make a person make $50,000 a year or make a person to get a certain amount of education. So we don't really have control over the setup, so we're really just observing what has already happened. And that can be a challenge, so that's one of the things we're going to talk about. Okay, some typical goals here. You can see these are they're all very economic feeling. So first one, estimating relationships between economic variables. So this is one of the main goals. So this would be describing how one variable influences or maybe just is related to another one. Testing economic theories and hypotheses. So what you see in econometrics a lot of times is starting with a microeconomic or macroeconomic or some other field of economics and creating a model based on the theory and then going from there. Forecasting, so this is being able to look ahead and predict what will happen. And then evaluating government and business policy. Okay, here's an example. This is an economic model created by Becker in 1968. And this hypothesizes what factors influence criminal activity. So one reason we might be interested in this is so that we can try to lower criminal activity. So the idea here is that the amount of time someone spends in criminal activity, which hopefully is zero for most of us, is probably related to how much money they're going to make from the criminal activity. So if you rob a bank, something like that, you could make a lot of money. So that might actually give you, you might decide that's enough reason to do it. Another one that might influence the hours spent in crime is how much you can make from legal employment. So if you can make the same amount of money in a day from going to your job as robbing a bank, you're probably just going to go to your job, but that's rarely true. So that's going to influence it as well. Any other income that you have, your probability of getting caught. So if you really don't think you're going to get caught, you're just like, hey, might as well. I don't have any penalty. And then the chance that you're actually going to be convicted. So most of us don't want to go to prison, so you might take that into account. How long you expect your sentence to be if you do end up in prison, and then your age as well. So this is an economic theory relating these different variables to criminal activity. You can see there's no functional form written here. So basically this is a theory saying we think all these variables are correlated with the time spent in crime. But for an econometric model, we generally have to have some type of functional form. There's one area of econometrics where you don't need to specify the functional form. It's really fun. It's called non-parametric econometrics or semi-parametric econometrics, but we won't get to talk about that today. Generally, you have to specify how your variables on the right are related to your variables on the left. So in this specific example that is coming from the theory, we've included the wage for legal employment, other income, the frequency of prior arrests, so this has to do with the probability of being arrested, the frequency of conviction, average sentence, and age. So you can see it's very related to that theory. In these models, we always have an error term. This is because there's always some factor that influences our variable on the left that we probably can't measure. This is also a way of just saying like randomness, the parts that you can't predict. So this could be called the unobserved determinants. In this case, that could be like moral character. That's going to influence how much time you spend in crime, but it's kind of hard to measure. Like, how do you describe in one variable how moral someone is? So that's kind of tricky. Your family background, that's kind of hard to measure too. There are ways of trying to describe those, but in this model, they have not included those. So they would be in your error term. Okay, how's R going for you guys? Pretty good? Okay, awesome. Okay, here's another example. So this is kind of a really common one. So this has to do with job training. So one thing we might wonder is if we send someone to a training program, is this going to increase the wages they make at their job? So you might guess that education probably influences how much you make. Your experience probably influences how much you make. And if you've received any specific training, that probably affects your wage. So this is an economic model. An example of an econometric model for this would be this model. So we would say that wage is linearly related to education, experience, and training. So they don't necessarily have to be linearly related, but for the introduction to econometrics, we usually start with them being linearly related. All right. You can also use these models for hypothesis testing. So we are very interested in these values, these coefficients. So beta naught, beta 1, beta 2, and beta 3. And the reason we're interested in them is they tell us how, for example, training is related to wage. And we may even wonder, is training related to wage at all? So then we would be asking, is beta 3 actually 0? And then this would tell us, like, why send someone to a training program if they don't end up making more money? So we can use formal hypothesis testing to actually test and see if that's true or not. Do you guys have any questions so far? Okay. All right, so we have to have data in order to estimate our coefficients here. There are different types of economic data. These are kind of the main ones, so cross-sectional, time series, pooled cross-sections, and panel or longitudinal. We're actually not going to talk too much about pooled cross-sections, but I'll say something short about it. So first type, cross-sectional. This is kind of like the data that you usually think of. So this would be like at one point in time, you might be surveying or measuring a bunch of people or households, firms, cities, states, even countries, and so on. So we generally can kind of assume that different people or firms or countries are more or less independent because unless you're maybe like your sister is also in the study and maybe you're telling her like, you know, I took this medication and it didn't turn out well for me or something like that, probably generally you're not really talking to each other. So generally the people are more or less independent. Now we do have to be careful with our sampling procedure. So basically, how do you collect the data? And we're not going to get to talk about that too much. That's like a whole class in and of itself. But one example of this would be like when you go to Fox News or CNN and they ask you, who are you going to vote for? That's probably not representative of the general population because you're already on their website. So we have to be really careful that the data that we have is random, and that means representative of the population. Okay, here's an example that you might see for cross-sectional data. So you can see there's a bunch of observations. We've got 526, so that's a pretty good sized data set. And then we're measuring their wage, their hourly wage, and then their educational level, their years of experience, their gender, and if they're married or not. Here's another example. So we might be looking at different countries. So here we've got 61 countries, and we're looking at different characteristics here. So their GDP, gross domestic product, and different variables there. Okay, time series data. This is another really common one. This is used a lot in macroeconomics and finance. Did one of you say you're a finance major? Okay, do you agree with that? Time series data?
Finance professor.
Yeah, maybe. Okay. Okay, we'll go with it. So what happens with time series data is that you're observing one variable or more than one over time. So you might be looking at the stock price daily, so how that varies. Or maybe the annual homicide rates. So kind of an ugly example there. And one aspect of these is that the observations are typically serially correlated. That means over time. That does not mean like your breakfast food. So over time, they're probably related to each other because like tomorrow's stock price is probably related to today's stock price. That's kind of how it works. Some of the things that we look at with time series is trends and seasonality. So trends would be like the overall trend that you see, like is it increasing in general? And then seasonality would be things like more cars tend to be sold in the summer, so you might see trends like that. Okay, here's an example of time series data. So we've got 38 observations, so sort of a medium-sized data set. Instead of looking at different people, we're looking at different years. So we're going from 1950 to 1987. So that's a pretty good time series study. We're looking at the minimum wage, the average coverage rate. The coverage rate has to do with what sort of percentage of the people are affected by minimum wage, the unemployment rate, and the gross national product. Okay, and then panel data. Panel's sort of the most intense. So panel's like a combination of cross-sectional and time series. So with panel, you've got a bunch of people or countries or firms and over time. So it's sort of a combination of them. Let me show you an example first. So here we have a 2-year study on crime city statistics. So one thing to notice here is that for each city, so like city 1 and city 2, whatever they are, we've got 2 years, so 1986 and 1990. So it's only over 2 years, but we've got 150 cities. So that's a great example of panel because we've got like the cross-sectional and the time component to that. Some advantages of panel data is that you can account for time invariant unobservables. So unobservables are like those things included in U in the error term. And having 2 time points allows you to sort of control for that, the things that don't change over time. So that's very useful. And then also it can be used for lagged responses. These are exactly what it sounds like. So this is like when you put more money into funding your police officers, that's probably not going to decrease the crime for maybe a couple years. So that's a lagged response because what we do at this time doesn't affect us until the next time period or even later. So you can see that with panel data. Okay, apparently I'm very consistent because I just said the example that's listed there. Okay, any questions? Okay, so one topic that we think about a lot in econometrics is causality. You've probably heard this like mantra basically, correlation does not imply causation. So this tells us that just because 2 variables are correlated does not mean that one is causing the other. So that's really important to keep in mind. So with the last example, having more police officers probably does cause a reduction in crime, but if we saw that happen, technically we don't actually know that having more police officers actually caused the reduction in crime. So that's something we always keep in mind. This also has to do with the notion of ceteris paribus. That's a fun phrase to say. This means keeping everything else the same. So how does variable y change if variable x is changed, but all other relevant factors are held constant? So that's called ceteris paribus. Okay, here's an example of causation. So you might wonder, if you're a farmer, by how much will the production of soybeans, or as we like to say, edamame, increase if one increases the amount of fertilizer? So we want to know, if I use more fertilizer, will I get more soybeans, more edamame? Our sort of implicit assumption here is like everything else doesn't change. However, most of the time you don't actually have control over that because you can't control the rain, for example. So if we could actually do an experiment, we would have like 30 plots of land. We would do the same thing with all of them except change the amount of fertilizer, and then we would know that the fertilizer actually affects the number of soybeans that we got. But most of the time in economics, like, we can't do that. Most people don't have that much land that they can actually do that. Here's another example. So if we are given additional police officers, how much will the crime rate fall? So in order to know for sure that the additional police officers is actually making the crime rate fall, we would need to compare basically two cities that are exactly the same except for the number of police officers that they have, which again is like, that's completely infeasible. You can't do that. Okay, so now we're going to talk about what's called the simple regression model. Simple does not mean easy. It just means that there's only one variable on the right side. So that's what that means here. Okay, this is the general form. So you've got your dependent variable on the left. It's also called the explained variable or response variable. On the right, you've got what is called the independent variable, explanatory variable, or regressor. And then you also have your error term. That's also called the unobservables, like we talked about, or the disturbance. Our whole goal here is to try to estimate beta naught and beta 1. Okay, so now we get to do some calculus. So thinking about differentiating with respect to x here. So for those of you who haven't taken Calc 3 yet, that means viewing x as your variable. So differentiating y with respect to x, well, beta naught goes away because it's a constant. Derivative of a constant is 0. The derivative of a constant times x is just that constant. And then if the derivative of u with respect to x is 0, then we get that the derivative of y is beta 1. And the cool thing here is this notation, or this statement, relates exactly back to ceteris paribus, because this says all other things remain equal when the independent variable changes. So that's exactly what our ceteris paribus statement was, that nothing else changes. And this also tells us like what beta 1 actually means. So this tells us how much does the dependent variable change if the independent variable is increased by 1 unit. So for example, for the wage equation, if your education increases by 1 year, beta would be how much we expect your wages to increase by. So that's what the coefficients tell us. As it says here, the simple linear regression model is very rarely, I'm going to add a very in there, very rarely applicable in practice because it's pretty much impossible to predict one variable based on only one other variable. So we use it kind of like a cool starting point, but we usually can't use it in practice. Okay, here's an example. So we talked about the soybean field and the fertilizer, and then the wage equation. But generally, you can't predict a person's wage just based on their education. I mean, you could, but you'd probably be really far off. Okay, So when is there a causal interpretation? So remember, we talked about correlation does not imply causation. So the main assumption that needs to be met in order to decide causation is the conditional mean independence assumption. This says that the expected value of u given any value of x, so like this means you're setting your value of x, so 12 years of education, then the average value of u is 0. That would have to be true. So unfortunately, there isn't a way to check this for sure. That's why we are, in general, very, very hesitant to decide causation, because it's really like we can't check this for sure, but there are ways to look at if it might be feasible or not. Okay, so in this example with the wage equation, this is unlikely to hold because people with more education generally are going to be more intelligent on average. That's kind of how it works. I mean, not always, but a lot of times. So there's going to be something in our U that is basically correlated with education, and that makes this assumption fail. So if you've got correlation between your U and your other variables on the right, that's going to cause this to fail, and that's bad. So that would mean that you can't conclude a causation. Okay. So let's talk about the population regression function. This is basically just the same thing like cutting off u. So if you take u off, then you're looking at basically your line here. Okay, here's a cool picture showing some data. And the data are the y values, so the x and the y. And then the population regression function, that's going to be the line that best fits that data. Okay, and then u, remember that's the error term. That's always the difference between y and the line that we're fitting. Okay, we're going to skip this one. This has to do with the properties of u, but we're not going to talk about that too much. Okay. So back to data, and we're going to do an example here in a minute. So the way we usually write our data is we've got a sample of n observations. So we've got x1, y1 through xn, yn. And our goal is to fit as well as possible a line through these data points. But basically our question is, like, how? So how do we find these betas? And generally how this is done is with least squares estimation. You may have heard of this. This is super common and very, very, very useful. Ordinary here means that you're treating all of these u's as the same. So there's also something called weighted least squares, and that's where you've got like a function basically in front of the u squared. So what we do is we take these things called the residuals. The residuals are basically the estimated values of the u's. They're going to be the true value of y minus the estimated value of y, coming from your population regression function. You want to try to minimize the sum of the squares of those things in order to force the line to be close to your data, because you want the line to go through the data really well. And this gives you your values of beta naught and beta 1. So you can see the formula that we get for beta 1 hat. Whenever there's a hat, it's like beta's wearing a hat. That means the estimated value. And the formula that we get is, as you can see, the sum xi minus the average of x, that's x bar, times yi minus the average of y bar, over the sum xi minus x bar squared. And then you plug into y bar minus beta 1 hat x bar to get your beta naught hat. Fortunately, we generally don't do this by hand. We let programs do it for us. Much, much nicer. So let's look at this next example. We're going to do this in Stata and in R. So we're going to look at estimating a CEO's salary based on this property of their firm. So it's called return on equity. And we're going to try to fit this. So we're going to use Stata first. So Stata is the most popular econometrics program, but it's expensive, and we actually don't have it here. I just happen to have a copy from when I worked there. It's a legal copy. So we're going to, I already wrote a script for this, so I called this salary. And, okay, let me try to move that over a little bit. Okay, so what we end up seeing here, this graph is a plot of all the data that I had in a data set for this. So this gave us a bunch of data points for the person's salary and the return on equity of their firm. So you can see a linear model actually looks pretty good here. We've got these outliers that they're pretty clear outliers. They're really far from the others, but the rest of it actually looks pretty good. It looks like there's kind of a linear trend there. And then looking at our output, so first what I did was I summarized the variables. So we've got 209 observations, and you can look at the mean of all those, standard deviation and everything. And then when you run your regression, this tells you the coefficient on return on equity is about 18.5. The constant term is about 963.2. And that's exactly what we've got here. So from using that data and then running the regression using the regress command in Stata, then we were able to estimate this. Let me make this a little bigger for you. So this tells us that if the return on equity increases by 1, then the salary is predicted to change by 18,000. Sounds pretty nice for that CEO. So, okay, let's try this in R now. So go ahead and open R. It should appear like in your apps, or if you have an older version of Windows like I do. Somehow I got out of getting Windows 10 on here. I'm not sure how I did that. But it might appear as an app, or you can just search for it, and you're going to go ahead and click on RStudio. So when you open that, it should look something like this. Now, yours won't have all this stuff in it yet. It'll be much more blank. Okay, were you guys able to get it to open? Okay, awesome. So next, you're going to get the data from the S drive. Okay, so go to the S drive. You probably have to go to Filer, so filer.cedarville.edu, and then you're going to go to the S drive and then go to My Folder on the S drive. So you're going to go to the S drive. SM stands for Science and Math, Holland, Data Science, and then you're going to go ahead and download salary.dta and put it somewhere you'll be able to find it. So anywhere on your computer as long as you can find it. DTA files are actually Stata files, so we're going to import this into R, and then we'll run this regression in R. Okay, so you're going to S drive, SM, Holland, Data Science, and then there you should find salary.dta. And then after you've got that downloaded, just make sure to put it somewhere that you'll remember. And you're going to first set your working directory. So there's a faster way to do this, but we're going to do it the nice GUI way, with point and click. So you're going to go to Session, Set Working Directory, Choose Directory. And now you want to go to that data. Okay, so I don't know why it's not in there, but it's okay. I already have it open. So you'll go ahead and just say open, and that will select your working directory. Okay, and then you're going to go ahead and import the file. So you're going to go File, and then Import Data Set. There's a faster way to do this too, but I'm just showing you the point and click way. Import Data Set from Stata, because DTA is a Stata file. And then you need to find that where you put it, where you just put it on your computer. and that's called salary.dta. And just say open, and say import. Okay, and then you should end up with a bunch of variables listed here. And we'll also show you that in your data set, so this panel up here is your data set panel, and it will tell you you've got 209 observations, 12 variables. Okay, how's that going for you guys? Logan?
Should the file appear in that folder when we're browsing for our directory?
Actually, you know what? I don't think it does. I think it looks like it should be there, but it doesn't actually appear. Yeah.
So then how do you...
Okay, then to actually open it, you're going to go File, Import, and then From Stata. So I'll pull the PowerPoint back up. So once you set your working directory, then you open it by importing the data set. Oops. Okay. Okay, how's that going for you guys? Pretty good? Okay. Okay, cool. All right, so now we're going to, oh, I should have left that. So now we're going to actually run the regression. This is the exciting part. So now you will type this. So one thing I want to say about R is the commands are not sleek. They're kind of like, they're just not intuitive because R is free. So they don't have it like super nice where the commands are like what you would expect. So for example, in Stata, the command to do a regression is regress, which makes sense. In Stata, it's LM. So like, how would you think of that? That stands for linear multiple. So we're doing linear simple, but that's fine. We can still use it. But it's free, so, and it's, I mean, it's really nice. So you're going to type that in there. What this does is it runs a linear regression, so linear multiple, where salary is on the left and return on equity is on the right. And this is telling it your data set is salary. And then you're saving the results into something called salary lin. I called it that for linear. Okay, so you're going to type that. Oh, I guess I should show you where. Okay. So you're typing that down here. So you're going to do your salary lin and then like an arrow, LM. Then you want to do your salary, regressing that on ROE, your data equals salary. Okay. Hit enter. It kind of looks like nothing happened. That's okay. Now you're just going to summarize that. So you're going to do summary, salary, lin. Okay, so that tells us your coefficients, your estimated coefficients. Okay. And then to plot it, you can do these next two lines. So go ahead and type those in there, the same place. And this first line, you may not need it, but the PAR line, that changes the margins of the graph because sometimes R does this thing where it makes the margins so large it can't graph it. Don't ask me why it does that, but sometimes you have to like remind it, like make small margins, please. So that's what that first line is doing. And then the second line is telling it the data to use and to plot ROE as your X, salary as your Y, and then AB line, that's another command that does not make sense, but that plots the regression line. Okay, so I'm going to go ahead and put this in R, and then I'll go back to the slides so you guys can see that. So that looks just like as in Stata. I mean, same data there, same line going through it. And so what you see from your regression is that the intercept, that's the coefficient or the constant that's by itself, is 963. The coefficient on ROE is about 18. That's exactly what we got before. Logan? Yep, leave it like that. Yep, will do. Okay. Anybody have questions? Okay. Now, one thing you may be thinking is, can't Excel do this? And yes, it can, but Excel cannot handle it when you have more than one variable on the right. So we'll do an example of that next. So then you'll start to see more of the power of R. So Excel actually can be a little bit nicer even when you only have one variable on the right, because the graphics look really nice in Excel. But once you've got more than one variable, which is basically real life, you're always going to have more than one variable on the right, then you're going to want to use like R or Stata or SPSS or something like that. Okay. Too many spelling errors? Did you get it, Laura? Okay, awesome. Okay. Other questions? Okay, did that work out for you guys? Okay, very cool. So let's go ahead and do an example where we have more than one variable on the right. And let's see. Okay, so let's look at this equation. Okay, so in this equation, we're looking at wage again, but we're looking at how 3 different variables can affect wage. So this is kind of similar to that job training program one we looked at, but this time we're looking at how does education, experience, and tenure. Tenure in this case means length of time that you've been at that company. How does this affect your wage? So in this example, we've actually changed it to be a natural log on the left. The reason you would do this is if, for example, you don't see a linear relationship. So what this does is it allows for there to be more of a percentage type relationship. Another way to say this is that log and experience, for example, are exponentially related. So if you were to graph wage on the y, experience on the left, you would see an exponential shape to that. By taking the log of wage, this makes them have a linear relationship instead. So let's try doing this. We'll go ahead and just do it in R. So you're going to do the same thing there. This is a little bit fancier because we're going to actually create that natural log variable that we're going to use on the left. So you're going to go ahead and open this new data set. This is called wage, so you're going to get that from the S drive as well. So you're going to go to my folder on the S drive, download wage.dta, put it somewhere where you can find it. And preferably the same folder where you put salary.dta so you don't have to change the workspace. So just put it in the same folder you put salary in. And you're going to import that again. So you're going to do File, Import Dataset from Stata. And once you do that, you should see the variables pop up. And the first thing you're going to do is create a new variable equal to the natural log of the wage. So we need that because that's what's on the left side of the equation. So to do that, you're going to use this like left arrow thing again. And this notation is sort of interesting. What is happening here is, see how we've got wage $sign. What's to the left of $sign is the name of the data set itself. What comes after the $sign is the name of the variable. So this is saying in the data set wage, I'm going to create a variable called ln wage. And what I'm going to put into that is the log. Log means natural log. So when you do log, it means natural log of the wage variable in the wage data set. Then once you've got that, you're going to go ahead and run the linear regression. And you can actually save that in whatever you want. So you don't have to use this wage lin. If you don't like that name, you don't have to use it. But just name that something so that you can refer to it. And you're going to do that LM again, linear multiple. Multiple regression is when you have more than one variable on the right, like we do now. So this really is a multiple regression now. And this is telling us we want to regress ln wage on education, experience, and tenure. So the way R does that is by putting pluses between the variables on the right. And then you say, comma, data equals wage to tell it, use the wage data set. When you do that, it's going to look like nothing happened, but that's okay. Then you're going to say summary wage lin. Now we can't get a super cool plot for this like we did on the last one because we're now in 4 dimensions here, so yeah, we can't really plot that. So unless you want to consider the 4th dimension time, and then that just gets very weird. Is that working for you guys? Okay, we'll give you a couple minutes to catch up there.
Too many spelling errors.
The spelling again. Maybe we should, as math majors, maybe we should have to pass some more spelling tests.
Are those capital L's or capital I's?
Oh, they're all L's. Like, are you referring?
Lowercase L. Okay.
Yeah, they're all lowercase L's. Yeah. Okay, so I'm going to go ahead and put this in. Okay, so I'm going to open that data set. Okay, so those should pop up there. We're going to create our variable. Run our regression. Looks like nothing happened, but then we summarize that. Okay, so that's really cool. So this tells us our intercept and then all of our coefficients. Did you guys get that? Okay. A couple of you are saying yes. Logan, do you have a question that I could maybe answer? Okay, sounds good. Anybody else? Okay. Okay, so let's look at what this tells us. Okay, so we should get, hopefully, for those of you who were successful, hopefully you got these values for your coefficients and your constant term. And so this would tell us that if experience were to increase 1 year, we would expect the percentage of the wage to increase by this percent, so about 0.004%. So when you have a log on the left, that tells you the percentage change instead of the absolute change. Okay. So one other comment, I think I need to finish up here pretty soon, but one other comment for those of you who have had a little experience with hypothesis testing, so if you've taken problem stats 1, or maybe you're in there now, then R does give you all the p-values and everything. So let's pull that back up. So looking at this column, probability greater than absolute t. Those are all the p-values. This tells you how sure you are about your estimates for your coefficients. And actually, R is really cool. I really like how they do this because they star it according to how sure the estimates are. So this has 3 stars. That means we're really, really sure. That's because there's a tiny p-value there. So that means we are really sure that this coefficient is not 0. So that was the coefficient on education. So what we found here is that we are really quite sure that education does affect wage, not a surprise. So that makes sense with what we know about life. And I think they actually are all significant here. So yeah, all these p-values are pretty small. And so it looks like we have what we would call a statistically significant model here. And it also shows you the overall p-value of the model. That would be from the F statistic for those of you who are familiar with that. It does also give you the R-squared value. R-squared basically tells you what percentage of the model, what percentage of the variation in Y is explained by the model. So I think I have that here. So R-squared is about 0.316 here. So this would tell us that the variation in wage about 30% of it is explained by this model. So that would tell us we could probably stand to put more variables in here because we've only explained about 30% of the variation. But generally, so the maximum possible value of r squared is 1. Generally, you're not going to get anywhere near that. So 0.3 actually isn't that bad. All right. Okay, so I have a lot more I could talk about, but I want to give you guys a chance to ask any questions, and then we'll probably wrap it up, and then I'll stick around and we can do more examples if you guys would like to. So do you guys have any questions? Yep, John?
The percentages that we have like on each variable,
Mm-hmm.
kind of like in the middle of there.
These things?
Yeah.
Mm-hmm.
Or the ones not in the parentheses.
Not in the parentheses, so these values?
Yeah.
Yeah, okay.
Those ones, are those like percentages of like our r squared value or just like in general?
Oh, gotcha. No, r squared can only measure the entire model at a time. So this tells us with all these variables, we've explained 30% of the variation in wage, but the coefficients don't really tell us how much is explained. They only tell us how much we could expect the wage to change if one of these variables changed. Okay, other questions? Thank you for your question, John. Mm-hmm.
Is there any, you talked earlier about causality versus correlation. Can you make any conclusions here?
Okay, good question. I would say probably not because, well, there's a couple of different ways you can think about it. So one way is to actually think about, are there things included in the error term here that may be correlated with the variables that are already included? So there probably are because we've only included 3 variables. So one thing might be something like family background. That's probably correlated with your education level. And since that's probably in your U and it's correlated, that would mean that we probably don't have causation. Okay, other questions? Okay. Yep.
Most of the examples that we've looked at so far have been mostly on more like, in economic terms, right, more of like a micro scale, like
Right.
examples. Is there anything, so like what's a common example of something applied to more of a macro?
Macro. Yeah, I have some time series examples a little later here. You can see I included just like a bunch of stuff. So let me see. Okay, so here's some time series stuff. Okay, so an example might be looking at like the unemployment rate and how that affects the inflation rate, things like that. Or here's an example with a lag model where you could be looking at like the tax exemption for having children for this year and last year and the year before, and how this affects the children born in this year, because it takes a while. So your tax exemption from the year before could actually affect this year. And here's kind of a small one, so this is kind of part of that model we looked at before. Okay, yeah. Okay, other questions? All right, so I think we will end here. It's about 6, so you're free to go. Thank you all for coming. I appreciate it. And if you do have any questions, I will stick around and try to answer them. Thanks again.